Now, another, I would say, big surprise of recent time that worth mentioning in our story would be incomplete without is reinforcement learning. Yes, reinforcement learning has existed for a while, and a book by Sutton and Bartow was very popular. And at one point, maybe 20 years ago, it was an active area of research with Markov decision processes and um, whatnot, lots of stuff. But then eventually, similarly to deep learning or neural network, people got tired, as we get tired of everything that is not fashionable anymore, and kind of moved on from reinforcement learning. Well, apparently not everybody. So reinforcement learning considers a learning problem slightly differently. Well, actually, very differently if you think about supervised problem. Because in a supervised problem, you or your algorithm, the brain, right, is only shown. Let me see. Yeah. Okay. Uh, so this is our algorithm, and it's only shown an example, and then say a label comes here. So input example, what should the output be? Input example, what should the output be? In reinforcement learning, the situation is different because the output is the action of an agent in the world. And the way the world responds, the action of an agent in the world changes the state, changes the world. And agent gets to observe the change of the state or the world as a result of the agent's action. And also the agent gets to observe reward, which could be positive or negative. So that's reinforcement learning in a nutshell. In 2015, I believe, not very famous yet at the time, but already quite known for some of their publications and for acquisition by Google, a British company called DeepMind started looking at the problem of playing Atari games plainly from the screen of the computer. Just input is the visual, the state is just the pixels basically. And another additional input is numerical, even though this picture shows graphics for the number, but the computer was actually getting number. And the choice was the joystick. What do you do with the joystick? So if we show them their system here is, again, the input is your image. Then here goes the convolutional neural network. Let's replace the whole brain and the whole decision process with the convolutional neural network followed by fully connected layers that make decisions about where to move joystick. Up, down, left, right, south, north, whatever, button pressed or no button pressed, or don't do anything. And once the system does it, immediately it observes the change in the world. Let's train the system by propagating the score or trying to maximize the score. And what do we observe, or what did they observe? Actually, if you look at a multitude of Atari games written over the years, DeepMind managed to demonstrate that thanks to convolutional neural networks, thanks to deep learning, and end-to-end training, we can train a model that can play all of those games with various accuracies, and most of them, or a lot of them, with superhuman accuracy. So this is below human level play. This is above human level play in some really above human level. So let's see how does the system work. Let's just watch for now. So the algorithm will play Atari Breakout. The most important thing to know is that all the agent is given is sensory input, what you see on the screen, and it was ordered to maximize the score on the screen, as I said. No domain knowledge is involved. This means that the algorithm doesn't know doesn't know any additional information. So 10 minutes of training, the algorithm tries to hit the ball back. Nah, not too good, right? But it's trying hard. Poor algorithm. Okay, much better. Getting better there. So, look, this seems trivial, but the thing to note, to observe, is that all that the algorithm see is sensory input, just a pixel. Okay, 240 minutes of training, half a day. Look what it does. Look what it figured out. Look, it figured out how to make a tunnel. And yep. So another interesting demonstration of what they did is Sequest. So why I'm showing it to you, because it's very interesting. The algorithm sees, quote unquote, remember the 1966 talk, 1966 task about computer vision by Seymour Papert, sorry. And what the algorithm sees is just 480, 520. The score is given numerically. The rest is given as an image. And look, it figured out to go up and get oxygen without ever getting the numerical value of oxygen, just the pixels, just the screen. And if it doesn't get oxygen, it cannot maximize the score. Obviously, it dies. And like when the score goes negative or the score goes down, that's easy to say, oh, of course, that's supervised learning or whatever, gradient descent. But look here, a different type of magic is happening because the algorithm is more powerful than whatever simplified assumptions you can make about it. And that's fun. That's a good start. That eventually allowed DeepMind to create AlphaGo and win the world champion in Go, and then create AlphaZero and surpass everything we could imagine about Go playing or chess playing or any of that board games. And then what was next? AlphaMaster, I think. No, AlphaMaster was in between. Well, anyways. Those are the advances previously unimaginable without deep learning, and that added to trust and deep learning. So another thing is this is from my work, and it's the third place at the NeurIPS competition with Misha Pavlov and Sergei Kolesnikov. They've done most of the work on this. The task was to train a model that is able to manipulate the muscles of that skeleton to walk as far as possible. And as you see, it's still not walking quite human-like, but it does walk, and which is amazing. So then the overall goal of this particular competition, and actually Sergey went ahead in next year and got to second place, and doing quite well with this research. But the goals of the reinforcement learning or operating in real world robotics, we could better understand our like recovery of our body after surgeries, if we understand how learning algorithms work on the muscle level. Because one thing is to formalize an algorithm of how to multiply numbers. Another thing is to multiply algorithm how to learn to walk, or how to formalize an algorithm how to learn to walk. We're still unable to do that. And I don't think we need to. Looks like neural networks can help us figure out at least how to perfect that.